Okay, the next problem we're going to be looking at is another homework problem or application problem, and that's problem 943. 943. Now, 943, we're going to be looking at finding the moment of inertia about the centroidal axis of this composite shape that consists of two standard shapes. So that means, just like we did for our centroids, we need to go to the back of the book and we need to find the information. So there's going to be some new columns that we're going to be looking at, because ultimately we want to find what is the moment of inertia of this composite about the centroidal x-axis and about the centroidal y-axis. So process-wise, it'll be very similar, except they were very generous in that they gave us our x centroidal axis, and then our y centroidal axis is going to go right down the center. So we've got that axis of symmetry right there, and then our, you can call it the YC as well. And then our XC they're giving to us, so we don't have to take the time to try to, or not try to, but to calculate the centroid. Okay, so we will start by drawing everything together here and start gathering the information on the separate items. So this is going to be problem 943. Okay, and so not that everything has to be perfect, but I'm trying to, you know, kind of give it some shape so that it looks a little symmetrical. Now our first shape, it said this is a C 250 by 22.8. So we'll be looking in the back of the book in our appendix to find that C channel, okay? And then the other shape, okay, this is going to be a wide flange, a W 360 by 44.6, okay? Now from the bottom of our part, okay, they gave us the X centroidal axis. Okay, so this is the X centroidal axis, and they gave us this dimension to be up from the bottom 231.9 millimeters. Okay. This is all going to be in metric units. So because it's in millimeters, it'll be kind of those big numbers. So we'll be noticing that we'll be probably using some scientific notation. Okay. All right. So now when we have standard structural shapes, it's kind of a little bit easier, if you would, to break it into its simple shapes or its separate shapes. So we're going to call number one the W360, and number two is going to be that C channel sitting up on top. Okay. Now, just like when we had simple shapes, the same process is going to happen. So we already picked our shapes. We need to establish the reference axis, which we sort of did. We know that the X centroidal axis is right here. And additionally, because this part is symmetrical, right down the center here is going to be that Y centroidal axis. So they already identified it for us, so we don't have to take the step of finding the centroid of the composite shape. So that's really nice. So we've already done our reference axis, which in our case is the centroidal axis of the composite. Now what we're going to do is we're going to gather the information about area, the moments of inertia of each one, and also distances that the centroid of those shapes are from the centroid of the composite. Okay. All right. So because these are standard shapes and we have our callouts, we're going to look to the appendix to grab that information. So we'll start with shape number 1, the W360 by 44.6. We're going to need the area. We're going to need the moment of inertia about the X centroidal axis. We're going to need the moment of inertia about the Y centroidal axis. And then we're going to need its dy, dy1. So it's going to be area 1, put little ones by each one of these. Now our dy1 is going to be from the centroid of our shape, okay, to the reference axis. So this is going to be dy1. So this is going to be C1, if you would. Okay. So we're going to need to find that information, and the back of the book will help us with that. So we are going to find our way in the appendix, and that's part of the second handout that I gave you guys. And we're going to find the W30 by 44.6 I-beam. So you want to look for this shape and then for that designation. So I'm going to, so it's a W360. There it is. Okay, so I found the start of the W360 callouts. So starting on page 459, you're going to notice that there's the I-beam here callout, which represents or resembles the one that we have. Now, on the bottom of this page is where the 360s start, W360, but on this page, it goes down to by 110. We need by 44.6. So we're going to turn the page, and you'll notice that it doesn't re-identify the W360, but it continues on. So these are W360s on the next page. And it's going to continue on, and we have the 44.6. Okay, so this, and this is on page 460. This is going to be the row that we're going to focus on. Okay. Now, we know we need to grab the area. So the area is going to be 5,710 millimeters squared. So we're going to put that in our A1. 5,710 millimeters squared. Okay. Now the IXC1. Now we have to look. The orientation of our shape is where we have the x-axis horizontal and our tallest dimension is vertical. That is the same orientation that this is. So when we look for our moment of inertia about the centroidal axis, it will be the same. Okay. So here's the x-axis. Here are the columns for the x-axis. And here's the moment of inertia, the very first column. Do you guys see that? Okay. So if I zoom in here, that's the capital I. Up on top, it says this would be times 10 to the 6th millimeters to the 4th. So we're going to be 121.1 times 10 to the 6th. Okay. 121.1 times 10 to the 6th millimeters to the 4th. Okay. Now, when we do the times 10 to the 6th, it means that we're moving our decimal point 1, 2, 3, 4, 5, 6, right to the right. If it's a negative value to whatever power, it will be to the left. Okay. So that's that one. Now we need to do it about the y-axis. And again, since our orientation matches the way ours is, that means we're going to go to the y-axis column, and I is the first column under there. Okay. So our I is going to be 8.16 times 10 to the 6th. So I'll zoom in here one more time. Y, here's the I, 8.16 times 10 to the 6th. And then our dy1, well, to find that dy1, we first need to know where the centroid is from the top or the bottom. And as we know, when we look at an I-beam, the second column here is depth. Depth is always the overall height. I don't know why they use that as the call out, but it is. That's what it is. So our depth is 352 millimeters. Okay, that's the overall height. So if the overall height, try to pull this out over here. The overall height is 352 millimeters. Then our D1 is going to be half of that, right? So if I know that this is half of 352, what is half of 352? 176 millimeters, okay? So then the difference between 231.9, right, and 176 is our D1 distance. And our D1 distance is the distance between the two parallel axes, which this would be the axis 4. And our D1 distance is, say it again? 55.9, good. 55.9 millimeters. Anybody else get that? I didn't check it yet, but I'll trust Jack. James said he's good. Okay, cool. Okay, so that's what we need. That's what we need for that first shape. Okay, now we're going to do the very same thing for the second shape. Okay, so can I fit it next to it? I'm going to try. So shape number 2, we need an A2. We need an IXC2. We need an IYC2. And then we're going to need a DY2. The DX, because it's a symmetrical axis here, is going to be 0 for both of these. Okay. All right. So now we need to find our C250 by 22.8. So I'm going to go further in here. We're going to find the C channel shapes. C channel shapes start on page 466. Okay, so that's the start of them. So they're these right here. And I'm a C250. C250. There they are. I'm going to be on page 468. And we've got C250 starting right here. Okay, C250 starting right there. And the designation after is a 22.8. So it's the bottom one. So let me get that. 2.8. Here's my line. Okay. All right. Now, this is not sitting in the same orientation as our part. Okay. We are sitting like this. Okay. So that means they're calling the horizontal, the way that we're having it sit, they're calling that the y-axis. Do you see that? So when we are looking at our x-axis, okay, that is going to be in the designation, our x-axis down here, but it's going to be the y-axis. So we're going to be using the y for that moment of inertia, okay? And then for the x, we're going to be doing the y. I don't know how to say that. So let's get our area first. 2,900 meters squared. 2,900. Millimeters squared. IXC. So again, because it's parallel to the x-axis, we are going to be on this axis right here. So that means that for us, we need to go down the y column. This is our IXC, which is going to be 0.949 times 10 to the 6th millimeters to the 4th. 0.949. So, times 10 to the 6th millimeters to the 4th. Okay. And now that means for our y-axis, which is vertical here, as we look, that is going to be the x moment of inertia. So we're going to go down this column, and now our x is going to be, or our y value is going to be 28.1 times 10 to the 6th millimeters to the 4th. So our y is going to be 28.1 times 10 to the 6th millimeters to the 4th. So we had to switch those around based on the way that it was sitting, okay? If it was sitting upright right here, the x's and y's would correspond. But because we were tipped like this, they were just flipped opposite, okay? All right. So now we need our dy2. dy2. So our centroid, if we look here on, I have to zoom back in here on the shape, where the intersection is for the x and the y axis here, that is going to be where our centroid is. And you'll notice based on how they're calling out that x bar value, that's from what would be the top of that C channel down to the centroid, okay? So what we need to do is our centroid for shape number 2 is going to be right here. This is going to be C2, okay? So the dimension they're giving us, okay, is this dimension right here, from here to here. All right, that's their X bar. And that X bar distance is at the very end of this column. It's 16.1 millimeters. 16.1 millimeters, okay? All right. Now, we need to find our dy2, and it is going to be from our centroid of our composite right here. This is our dy2. Okay. So we know this C channel is sitting on top from the bottom, right? 352. We know that from the very top of it down to its centroid, it's right here, but we need to know what this thickness is, right? And if you recall from when we did the centroid stuff, that's web thickness. Okay, web thickness. So web thickness is 6.1 millimeters. 6.1 millimeters. So this distance, I'll go on this side. 6.1 millimeters. Okay. So if we look, if we start at the bottom here, kind of do continuous dimensions, we'll see if we can get this. So if we do, actually from our centroid, we go down to 231.9, down to the bottom. Then we're going to go up underneath, go up the 6.1, and then down the 16.1, and that'll be the distance left over. You guys agree? So this is what we're going to do. We're going to do this in sequence. So we're going to have a negative 231.9 millimeters. Okay, that's my down from my X. Now I'm going to go up positive 352. Okay, and I'm down underneath here. Now I'm going to go up again 6.1. So that's going to be a positive 6.1 millimeters. So I'm now at the top of my C channel, and then I'm going to come down negative 16.1. Do you guys kind of follow that? Does that make sense? So now my dy2, what do we get when we take negative 231.9 plus 352 plus 6.1 minus 6.1? Say it again, Josh. Okay. That sound right? Did anybody else get that number? Okay, and just double checking, you kind of see how we did that. So we started at our centroid. We went down to the bottom. We went up underneath. We went the thickness and back down to that centroid. Okay, so that gives us our leftover amount, our gap in there. Okay, so now for both of these, we didn't do these, but our dx2 is going to be 0. And our dx1 is going to be 0. And that's because we have this axis of symmetry. There is no offset left or right for either one of those centroids. They're on the y-axis. Okay. Then now we are ready to, we've gathered all our information. We're ready to do the calculation for the moments of inertia about the centroidal axes. So let's first write those out. And we'll leave space so that we can add them. So the total moment of inertia about the centroidal axis is going to be the summation of the IXCs plus the summation of the area times the dy squared. We're going to leave some room here so we can write the numbers in. And then the other one that we're going to do is the IYC, summation of the IYCs plus summation of the A times the dx squared. And then we'll leave a little space. And we have to make our chart. I think I need to do landscape. I don't know if I'm going to get all my columns, so I will. I'll do a fresh piece of paper. You guys might get them because you guys, I know, write smaller than I do. You guys are much better at that. Maybe because my eyes are getting bad. I think I do write bigger as I'm older. Your eyes start going bad, so you got to write everything bigger. Okay, my first column is going to be my shape, right? What do we want our next column to be? We've done this often enough, right? Shape, we want to do area? Sure. Area, and that's going to be in millimeters squared, right? So we'll put our units up on top. Okay, what do I want to do next? You want to do dy and dx? Sure. dy, which is going to be millimeters. Okay. dx, millimeters. Okay, now what? So if you look back over here, we did our A's, our D's, right? So should we do a column for each of the A times the dy squared and the A times the dx squared? Yeah. So this is going to be A times dy squared, and that's going to be millimeters to the fourth. A times dx squared, millimeters to the fourth. Okay. And what's left over? I need 2 more columns. Yep, my moments of inertia about my x centroidal axis and my y centroidal axis. So IXC millimeters to the fourth. And IYC millimeters to the fourth. Yeah, I needed landscape. Definitely needed landscape. So I'm going to have a shape number 1 and a shape number 2. I don't have a shape number 3 this time. So I can make this a little bit shorter, right? There we go. There we go. Okay, so now I'm going to go back to my shapes, and I am going to grab the information that we collected. So what was nice was we did it all on the same piece of paper because these were those structural members that we didn't have to do any separate calculations. So I'm simply going to put in my area number 1, 5710, my area number 2, 2900. My dy for my number 1, 55.9, and my dy for number 2, 110.1. My dx's were zeros for both, which means that my a times my dx's are going to be 0. I'm going to leave this here. I'll let you guys calculate that in just a second. And then I'm going to fill in my ixc's and my iyc's. So my ixc1 was 121.1 times 10 to the 6th millimeters to the 4th. My ix2 was 0.949 times 10 to the 6th millimeters to the 4th. My YC1, 8.16 times 10 to the 6th millimeters to the 4th. And IYC2, 28.1 times 10 to the 6th. Now, as we look at our moment of inertia equations, we need to sum up the columns for each one. So we need to sum the IXC, the IYC, and then the summation of the A times the DY squared, and the summation of the A times the DX squared. So these are going to be our summations. We don't need any of these three, but we do need those four. So go ahead and do that last calculation in your summations, and then you can fill in, but I'm going to translate these over here. These I didn't do since last year. $17.84. Bless you. So it looks like what I've got here are good answers. I did check them to the last page in our practice problems. The answer is there for problem 943. And these do indeed match. So as we look here, here are your answers on the summations, and then filling in the appropriate columns. So the IXC, the summation will go here, plus A times the DY, that goes there. So adding those two together, your moment of inertia about the I centroidal axis of the composite is going to be 175 times 10 to the 6th, okay, or 174.99. And then for the moment of inertia about the Y centroidal axis of the entire composite, 36.2 times 10 to the 6th millimeters to the 4th. Okay. All right, any questions there? Okay, I'm going to stop the recording.